All right, thanks for joining us today. I announced this in class yesterday, but just as I'm thinking about it now, I'm not sure that I sent out the email and posted an announcement. But our exam will be next Thursday, again at 6:30 p.m. I'll put that information up on the website because I think that I did not do that yesterday. The exam will cover everything basically from the beginning of open systems to the end of the 4-component Rankine cycle, like the example that we did in class yesterday. So now that we've kind of bookended what's going to be on the second exam, I'm going to run through that content again today. So today's content will be exam review for the second exam. So generally, the things that are on this exam are open systems, right? So we talked about the general open systems, right? So this eventually we start to use with cycles like Rankine cycles, but we end up doing those very quickly, right? So we do 4 open system control volumes in the Rankine cycle that we've learned already, right? We learned about entropy in the second law. So you could get maybe as part of a long answer question, maybe we'll ask you to do some work with the second law of thermodynamics. But in the multiple choice type questions, you might also see, you know, some conceptual questions about, you know, what is entropy, right? What is the second law telling us? We learned about Carnot cycles, right? So how do we do ideal heat engines, heat pumps, and refrigerators? How do we characterize both real and ideal systems? So if they're heat engines, we talk about thermal efficiencies. And if they're temperature management cycles, then we talk about coefficients of performance. Then we talked about isentropic efficiency. So how do we deal with turbines and pumps that are not ideal, that are real, right? Either how do we look at the real device, see what its performance is, and then define what its efficiency is, or we can know its efficiency and then find the ideal outlet and use the efficiency to get that real outlet state. Finally, we talked about these 4-component Rankine cycles, right? So basically, as we'll talk about, right, these are, you know, they have a turbine. The turbine's the business part of the whole show, right? So it's trying to produce power. That's the whole point of the cycle. And then we use those other components, the condenser, the pump, and the boiler, just to get back to the inlet of the turbine again so that we can continue to make power, right? And we talk about thermal efficiency in terms of those Rankine cycles, and we can compare the real thermal efficiency to the Carnot or the ideal thermal efficiency. So I think I said this before last exam too, but generally, if you feel totally lost in this exam, what I would do is I would write down conservation of mass, because that'll let me figure out what's going on with the mass in my control volume. I'd write down, well, I guess the first point here, I guess, was not do conservation of mass. The first point is, what's the part of the universe that you're interested in, right? So if it's a Rankine cycle, you got to say, oh, well, I'm interested in the turbine, right? Because I'm interested in the power produced. Or I'm interested in the turbine and the pump because I'm interested in the net power. Or maybe I'm interested in the turbine and the pump and the boiler because I'm interested in the thermal efficiency, right? So what's the part of the universe that you're interested in? Then what's conservation of mass, right? So oftentimes we end up kind of doing this in our heads because we see the system is at steady state with one inlet and one outlet, at which point the mass flow rate in is the mass flow rate out. But sometimes just writing down your assumptions, not only are you demonstrating that you know what you're doing, right, which is sort of the purpose of a test, right, but you're also then kind of getting the ball rolling, right? You're starting that inertia towards the solution, right? Then we want to ask what happens to the energy. So we do a first law analysis. Again, I'm always going to encourage you to start with the base version of this equation, which we'll talk about in a bit. We remember that the equation is actually different if it's a metric problem or if it's an imperial problem. And then the reason we start with the base level of the equation is because then we can very clearly demonstrate what are the assumptions that we're making about the system, right? So even if you don't know what's going on in the problem, write down conservation of mass, write down the first law, maybe start making some assumptions, and then before you know it, you got a symbolic solution, right? Now, sometimes you might get a question like, is this process possible? Or maybe you'd get a part of a long answer problem where it's, determine the rate of entropy generation, right? Which is ultimately on the road to asking, is this process possible? And if you get a question like that, then in addition to conservation of mass in the first law of thermodynamics, you might have to write down the second law of thermodynamics. Now again, start with the base level of the equation, make your assumptions, cancel out terms, and you'll be left with some kind of symbolic solution. Right? And then finally, I guess what's not on here, right, is always after we do all this, we'll get a bunch of symbolic solutions, just like we did in the example yesterday. And then we say, what's the fluid? How do I go through and fix all the states that I need to fix so that I can get numerical answers for these problems? So conservation of mass, right? So that's the first equation we're going to deal with after we've determined what part of the universe we're interested in, right? The base level of this equation, dm by dt, is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. Assumptions that we'll often, but not always, make might be, if it's at steady state, then the dm by dt term goes away, right? If there's only one inlet, then the summation sign here goes away. If there's only one outlet, then the summation sign here goes away. But you could easily get a case like this where you get one inlet and two outlets. So you might not always be able to make these kind of assumptions that we usually make, right? That's why there are assumptions we usually make and not assumptions we always make. So here are the common assumptions, right? Steady state, one inlet, one outlet. And if we can do that, then we can say that the mass flow rate in is equal to the mass flow rate out. And if it's the 4-component Rankine cycle that we know about, and all the components are at steady state with one inlet and one outlet, then what we learn is that all the mass flow rates that are chained together in series like that are the same. So, because the outlet of one component is ultimately the inlet of the next component. Right? So that's how we deal with conservation of mass. Next, we have to deal with conservation of energy, or the first law of thermodynamics. This is a really good one if you're lost. Write down this equation, right? Because it's thermodynamics class. You're almost always going to have to use a first law analysis. Like, I can't imagine a long answer problem that you would see on an exam where you won't use the first law. So if you're lost, right, write this down. You got 30 minutes anyway, right? So, you might as well write something down. Like I said, my heart breaks a little bit always when I see a blank page, right? Or I get nothing for a part of a question, because usually there's at least something you could write down, and getting those first, 30 to 50% of the points on a question, you don't have to write all that much down, right? So start, writing down one of these governing equations for whatever problem you're looking at. Right, if we want to zoom in here, we got dE by dt. This is the amount of energy that's being stored or depleted in our system over time, or the rate at which energy is being stored or depleted, because it's a rate equation. When we're talking about problems with this equation in Thermo 1, we're always going to be talking about steady state problems. So this one is going to go to 0 in every case. Q dot, right? So this is heat transfer rate into the system. This is follows that hip to win sign convention, so heat in is positive. The power term here, right, that's work rate, right, or power. So that also follows our hip to win sign convention, so work in is negative or work out is positive. This is basically, this term survives in your equation if you have fan blades inside your system, right? So when you have a turbine, you have steam, or we'll learn later, air expanding through the turbine, and it runs over these fan blades, and that's what puts that sort of torque on the shaft, which makes it spin, right? That's how you generate the power. And in a pump or a compressor, it's the opposite, where you plug that pump or compressor into the wall, you flip the switch, and that makes those fan blades spin, right? And that adds energy into the system, right? So basically, if this term survives, you're looking for fan blades or paddle wheels or something inside the system. Now, this term, which we could break up into 3 parts, this is the rate of energy coming into the control system because of mass transfer, right? This is why before we have to deal with energy transfer, we have to talk about mass transfer, because we learned early on in this class that mass itself, because it has some temperature and a pressure, if it's a fluid, then, it's going to have some amount of energy that it carries with it, right? So this is the energy that comes in with the mass, and this is the energy that goes out with the mass. I'm not super consistent on my subscripts here. Sometimes I use E for exit. Sometimes I use O for outlet, but it's the same thing. Now, in these terms, these mass flow rate terms, there's three different parts of energy that we're generally concerned with here. The first is the specific enthalpy. So this is what's going on because of the specific internal energy, the pressure, and the specific volume. Right? We remember that's the definition of specific enthalpy, is U plus PV. This is going on, so this is like, what's the fluid? This is what we're looking up in the textbook, right? So hopefully that's not a shock, right? Then we've got this kinetic energy term, right? Or change in kinetic energy, between the inlet and the outlet, right? If this one survives, you got to worry about units, right? Because if here, this is in metric, right? If your velocity was in meters per second, then this term would be in joules per kilogram. But H, when we look it up in the table, is kilojoules per kilogram. So you're going to have to divide this term by 1,000. Remember, there was an example we did when we first started talking about turbines in the first law, and I demonstrated to you numerically that the kinetic energy term in that case was not important. Potential energy could sometimes stick around as well, or you could be asked to demonstrate that it's not important. It's got that same problem as the kinetic energy, where here, if Z is in meters, then you'll get joules per kilogram instead of kilojoules per kilogram. So you'll have to divide by 1,000, right? So basically our spidey sense has got to start tingling anytime we're left with velocity or kinetic energy or potential energy terms. Problems are always more complicated when you're dealing with imperial units, right? So here, it's going to be those two terms that cause us difficulty with units in the metric version that also cause us difficulty in the imperial version, right? So here, the first thing that we have to do is we've got to take these terms and divide them by GC, right? If you don't remember what GC is, right, this is how we got to, with Newton's second law, how 1 pound mass has a weight of 1 pound. Right, so we take that and we divide by 32.2, but it's got special units, right? So that we can not only get rid of the acceleration, right, but we can also convert that pound mass into pounds force. You don't have to memorize that, although you might end up doing it if you do enough of these problems, because it's on the equation sheet, right? So trust the equation sheet. We've been using it for many years. I made it like the second or third year that I was here, and it's basically been the same for the last 5 years or so, right? But it's an open exam because we're doing it online. So you're also welcome to make your own equation sheet, right? Or your own equation sheets. And doing so, I think, is a good form of studying because it gives you the opportunity to really think about what's important and what do I want to put on that space. So if you are making your own reference materials like that, I would challenge you to constrain yourself on the space, right? To really think about what's important, right? And how can you collapse things down so you can start to look at all these problems kind of like they're the same problem, right? So again, units here are important. Not only do we have to divide by GC, but if my Z term is in feet, or my velocity term is in feet per second, then here I'll get foot-pounds per pound mass. But H, when I look it up on a table, is going to be in BTU per pound mass. So I have to take this number and divide it, I believe, by 778 foot-pounds per BTU. So it's still going to be those same two terms, right? It's still our spidey sense or the hairs on the back of our neck are still standing up when it's these two terms, the kinetic and potential energy terms. But the strategies for dealing with them are a little different if we're using, feet and pounds versus if we're using meters and kilograms. Right, so the units here are important. So what are the common assumptions that we'll use here, right? So almost always, or really always, I think in Thermo 1, we're going to say that this is at steady state. Then we'll often, but not always, say that there's one inlet and one outlet. So if there's one inlet, this summation sign goes away. If there's one outlet, this summation sign goes away, right? But remember when we did when we looked at the heat exchanger last time to find the mass flow rate of the cooling water, then we didn't do this one inlet, one outlet stuff because we looked at the whole condenser, which has 2 inlets and 2 outlets. We'll often say that the change in kinetic energy is 0, but we have to know how to deal with that with the units, right? Same with potential energy. That's usually crossed out, but know how to do that because I could certainly ask you a problem where you have to do that. Either as a multiple choice question and say, what's the kinetic energy at this point? And the answer's in kilojoules per kilogram or even kilojoules per second, right? So it's in kilowatts, right? There's all kinds of ways that we can ask this. So you have to know how to numerically compute that. Then typically with open systems, we'll assume that they're simple systems unless we're told otherwise, right? So a simple system means either heat transfer rate or power sticks around, but not both. Again, I can sort of disrupt you from this particular assumption by giving you something like a turbine that has some kind of heat loss with it, right? And then your equation won't just be W dot equals M dot times H in minus H out. It would be W dot is equal to Q dot plus M dot times H in minus H out, right? But you don't have to memorize all the different potential cases, right? I don't like memorizing things. I find that I'm not good at it. I want to understand how to get to a place. So that's why I always start with the base level of the equation and I think about my assumptions and then I'll get the right answer, right? Because sometimes turbine power is not just M dot times H in minus H out. Now, when we talk about something like a Rankine cycle, we'll typically neglect anything that's going on in the lines in between the different components, and we'll also neglect the frictional losses as we're moving through, say, the boiler or the condenser. So what that means when we say neglect friction losses, that means the pressure is not changing just because the fluid is moving through a line. That's not real, right? The pressure actually does decrease because conservation of mass tells us that the average velocity in the pipe has to stay the same. So we can't slow down. Friction can't take from kinetic energy inside a pipe. So what happens is that, at least if you're at steady state, what happens is that it takes from the potential energy that's locked up inside the pressure, right? Then we also neglect heat loss in the lines because just because we don't have to, that way we don't have to do another control volume just for the lines that are connecting, say, the boiler to the turbine. So after I do this, after I look at the first law and I make all my assumptions, I'll almost always be asking myself, how do I fix the state, right? What's going on with H or delta H, right? And to do that, I need to know what the fluid is. So the first question here is, what's the fluid, right? So if it's water or something like it, could be a refrigerant or something, then I got to ask myself, what's the phase, right? So I only want to use tables probably if it's a two-phase mixture or a superheated vapor. In this particular note, because this was done a little while ago, it talks about the tables that are available in the FE handbook. We've talked a little bit about the FE exam here in the US. If you want to start on the path to becoming a professional engineer, sort of getting certified, we used to give as the reference material for the exam the FE handbook, right? So that's what you would get if you were writing that test. But I think we've since gone back to just, using spiral bound copies of the tables, or now that we're doing, these exams online, then you have the digital version of the tables that are available on my courses, right? So you want to look in the tables if it's water or something like it, if you're two-phase or if you're a superheated vapor. If you're a subcooled liquid, there's a couple things that you can do. If it's a subcooled liquid with a low temperature change, you can just say Cp times delta T. This is fine as long as it's liquid on both sides of the process, right? So if you've slipped, between state 1 and state 2 into the two-phase vapor region, then you can't use this equation. Once any part of the fluid becomes compressible, right? So once you get any bit of vapor in there, you can't use that equation, right? But if it's liquid to liquid, so if I think the example we used yesterday was the idea like we're pulling water out of something like Lake Ontario at 4 degrees and it runs through our power plant and we put it back into the lake at 25 degrees, right? So we had this 21 degree temperature change. That's not a big temperature change. It's liquid to liquid. So you could use delta H is equal to Cp delta T. Or you could say, you could go to HF at either one of those temperatures and get a value for delta H. Then we've got this special case, and this is one of those things, sometimes students will ask me like, oh, what's a common mistake that people make on this exam, right? So one of the common mistakes that people make on the exam is this idea that across an ideal pump, delta H is the specific volume times the change in pressure. So first, people might just not remember this, right? That this is the ideal pump equation that we use to find delta H. Second, they might mess up the units, right? So always, always, always track your units in your calculations, right? Because if you take this specific volume, which is in meters cubed per kilogram, and you multiply by a delta P in, say, bar, you're going to get some super weird unit, right? So in this equation, I always want meters cubed per kilogram multiplied by kilopascals. So I turned my pressure into kilopascals. It's going to be worse, as always, if this, which I think is in cubic feet per pound mass in the textbook, multiplied by pressures often in PSI, right? So you're going to have to mess around with your units so that you get delta H. You want delta H in imperial to be in BTU per pound mass. So that one's going to be a little trickier. You'll have to work your way through the units. Now, if you have an ideal gas, you can assume that it's constant specific heat. Although if it's a long answer problem, I will tell you whether to use constant or variable specific heat. But if it's constant specific heat, then you'll take Cp times delta T. Right? And if it's variable specific heat, you'll take delta H is equal to delta H, and you'll go to table A22, assuming that it's air. And if you know the temperatures, then you'll use the table and the temperature to find H for that specific state. Sometimes when we're fixing H across, say, a real pump, maybe we can find delta H for the ideal pump this way, right? This would give us P4 or H4S, right? Or delta H across the ideal pump. And then we can use the isentropic efficiency if it's given, right? So I think in that last problem, we were told that the pump efficiency was 85%. So then we use the ideal delta H and the efficiency of the pump to find the real delta H, which would let us find H4 instead of H4S. And you can do the same thing across a turbine as well. Right? So this brings us into our next topic, right, which is this idea of ideal versus real turbines and pumps. This idea that we have this thing called isentropic efficiency, right? So what we do is we compare, say, the real turbine, where the entropy is increasing, to an idealized version of the turbine that has the same mass flow rate, goes across the same pressure difference. How much power would that ideal turbine produce? And how much power are we producing in the real turbine? And if I take the real turbine power divided by the ideal turbine power, I can define an efficiency for the pump or for the turbine, right? The pump works a little different because we're consuming power there. I probably have these equations on the next sheet, right? This is also why we moved from TV diagrams, which we used for closed processes, to TS diagrams here. We like the TS diagrams because graphically, I can see that if I have a turbine or a pump that's steady state, adiabatic, one inlet, one outlet, and ideal, then delta S across that ideal turbine or pump will be 0. So a vertical line for a turbine or a pump is telling me that the turbine or pump is isentropic, which probably means that it's ideal. Right? Like I said, we have the purpose now of these isentropic efficiencies is to compare the real device to the ideal device. Right? Now, turbines are producing power. So what happens is in the real turbine, you lose some power because of things like friction in the bearings. Right? So the real power of the turbine is less than the ideal power. Right? These isentropic efficiencies are always going to give you a number less than 1 or less than 100% if you want to multiply by 100. Right? So for turbines, it's real divided by ideal. But for pumps, because pumps are a cost to the system, right, then the cost to the system is higher in the real case. So the real power goes on the bottom. You might end up memorizing this just from doing it enough times. But don't worry, it's all there on the equation sheet. So you can just print out the equation sheet that's posted on my courses, right? Or like I said, make your own equation sheet and put this on. But if you do make your own equation sheet, just like triple and quadruple check that you're writing the equations down correctly. Because I would hate for you to get something wrong because it was written wrong on your equation sheet. I think this happened to me in my first year physics exam, because I came out of that class in that final exam and I really felt like I wrote a perfect exam. And then I was walking home, right, and talking to my friends and stuff, and it hit me for a second, and I was like, oh, I forgot to divide kinetic energy by 2, right? Just a stupid mistake, right? Because, I didn't have it on an equation sheet or I didn't write it down properly. So try to avoid those kind of clerical errors if you're making your own reference materials. I was pretty upset when I realized that. But not as upset. The worst exam story. This was, I think it was maybe our controls class. And, we were writing exams in person. And my whole class, right, we come out of the exam and we're walking back home, right? And a couple of us lived in kind of a similar off-campus location. And then I saw 3 of my other friends and they're walking toward us. And we're all like, where are you guys going? What are you doing? And they're like, oh, we're going to the exam. And it's like, well, the exam just ended. So you guys are in trouble, right? So they sprinted in and the professor let them write the test. But I imagine that they weren't in the best mental state when they were writing that exam. So I never asked them how they did on it. But I would not be surprised if it turned out to be a difficult exam for them just because they were rattled at the beginning. Right? So try to avoid that, next Thursday. Try to, do whatever you can to have a calm day beforehand. Right? Make sure you get some good sleep. I'm a big believer that sleeping is the best form of studying. Right? Make sure that you're fresh and ready to go. Right? Now, back to the show. Right? So the next thing that we talked about, right? We kind of made this, it might have felt a little bit like a detour at the time. I always struggle a little bit where to put this content in. But we started to talk not just about open systems, but about this. We started to talk about thermodynamic cycles, right? And, we were introducing this concept of the second law, right? And how there's different ways to look at the second law. And one of them comes from Calvin and Planck, right? So these are giants in the field of physics and in thermodynamics, right? And what they told us is that, yeah, you can make a heat engine, right? You can take heat in, right, and turn it into work, right? But you can't turn all that heat into work if you want your engine to run for any long period of time, right? You need to, well, really, even if you don't, even a short period of time, you're going to lose heat, right? But you have to cool your engine down, right? Like I said before, you don't want to be that person on the side of the road, right, pouring their Nalgene bottle on top of their engine to try to cool it down because they lost their radiator fluid or something, right? And that's because we need to reject heat in order to run one of these heat engines. And that's a pity because we know that the energy in, right, the first law for a closed system tells us that the energy that comes in terms of this heat transfer, has to go out, and only the same amount of energy can go out if we're at steady state. So here, there's some energy coming out over here, but there's also energy going out by heat transfer. So we've got this thing where because we have to cool the engine down, we can never get 100% energy efficient, right? And probably not even all that close for a mechanical heat engine. Another way to look at the second law was brought to us by Clausius, right? So Clausius wasn't looking at heat engines. He was looking at, this idea of thermal management devices, right? This guy, it always kind of spooks me out, the eyes in this picture. It kind of reminds me of my grandparents. This was like the style when they first had pictures or something. Like, you had to look really angry, like there's nobody like smiling in pictures. You look at old pictures, they're all like very stern-faced, right? So I got lost in his eyes, I guess, right there. I looked over and it just always spooks me out a little bit, right? So here, what Clausius told us is that, yeah, it's possible to make a device that removes heat from a colder place and ultimately dumps heat in the hot place, right? Now, my heat transfer professor told me that there's, this thing that he talked about as being the 0th law of thermodynamics, which is that heat is always transferred from high temperatures to low temperatures, right? And that's true even in this device, right? Even though it looks kind of like we're transferring heat from a cold place to a hot place, we do that by making a machine where half the machine is colder than the cold place, and then the other half of the machine ends up being hotter than the hot place. So here we're accepting heat here and rejecting heat here. Now what's going to happen is if you try to do this passively, right, your cold place would eventually heat up, or your cold side of your machine would eventually heat up. Your hot side of the machine is eventually going to cool down, right? And it's all just going to get to equilibrium, and you're not going to transfer heat anymore. So what do you have to do, right? You got to plug this thing into the wall. So Clausius said you can't do this and produce power. You can't even do this and break even. Instead, to do this, you have to plug this thing into the wall and add some work or some power in order to run this cycle and keep the cold part of your machine cold and the hot part of your machine hot, right? So that's what Calvin and Planck and Clausius told us about the second law. Right, so then we talked about this idea of the elapsed time version of the second law, which we rarely, if ever, use, right? Delta S is equal to Q over T plus the sum of the mass in times S in minus the mass out times S out, and that's going to be equal to the entropy generated, right? But just like in the first law, we'll typically for open systems, well, really always for open systems in this class, be talking about the rate form of this equation. Right, so now it's the entropy that's being stored or depleted in the system. We've got energy coming in or out with heat transfer, or entropy coming in or out with heat transfer. We've got entropy coming in or out with the mass flow. And now we have this entropy generation rate, right? So I guess this is just going to say the same thing, right? So how much entropy is being stored or depleted in the system? The rate at which entropy is entering the control volume because of heat transfer, right? This is communication with the rest of the universe. This is why a condensation reaction doesn't break the second law, right? The important things here, right? So the Q dot term is still follows the hip to win sign convention. This temperature is the temperature of the surroundings, and it's got to be an absolute temperature because it's not a temperature difference, right? So that's another, common things people mess up on the exam, this term. And I know people mess up this term. So, sometimes you can draw a control volume to get rid of this term. And if you can do that, I'd encourage you to do it. But I know that makes the problem easier, and it takes away your ability to demonstrate that you know how to deal with this term, right? So expect to demonstrate your understanding of how to use that term. Then we have the mass flow, or the entropy that comes in with the mass flow rate, the entropy that comes out with the mass flow rate. And then the whole reason that we're here, right, the whole reason that we use the second law like this is to find this entropy generation rate. What we know about the universe is that the entropy generation is always increasing. There's always more and more entropy. That means that the entropy generation rate, it could change, right? The slope of that line could change, but it's always positive, right? So sigma dot always has to be greater than 0 if it's something real, right? There's this edge case, right? The limit where sigma dot is equal to 0. That's not okay. You can't actually do that. But that's still useful because that's like the target. That's the thing you can strive for. That's the ideal process, right? And then if sigma dot is less than 0, then you can't do that, right? Then that process breaks the second law and means that it cannot happen, right? Or it shall not pass, right? That came from, I got my notes for this class from, I think his title is maybe Vice President of Research or something now. He used to be the department head here, Ed Hensel. And it said just something about, the process cannot pass or something like that in the thing. And it, I thought about the Lord of the Rings. So that's why I always put that silly little joke in there. And hopefully, right, partly I put the jokes in to amuse myself, right? But the other thing, I hope that they're there, not necessarily to be funny, although I do always appreciate the sympathy laugh. But, the stupid little jokes hopefully will help you to remember things. So, I put them in hopefully at points that I think are important, right? Common assumptions that we're going to make here for the second law, right? Steady state. So this one, again, in this class, we're always going to stay steady state. Sometimes a process is one inlet and one outlet, and those summation signs, one or both of those summation signs might go away. I can make my life a lot easier if I can draw my control volume in a way to make the process adiabatic. But like I said, that's the one that people are going to mess up. So I'll probably give you an opportunity to demonstrate that you know how to deal with that term. Okay, once we're done with this equation, then we're going to be in the point, right? We'll have a symbolic solution and we'll say, well, what's the fluid? How do I find S or delta S? Right? So again, if it's a two-phase mixture or if it's a superheated vapor, then you can use the tables, right? And if it's a subcooled liquid, you can use the subcooled liquid approximation where S of some temperature and pressure for a subcooled liquid is approximately equal to SF of that same subcooled liquid at that same temperature, right? So we say it's a weak function of pressure. For ideal pumps and turbines, we know that delta S is equal to 0. So here I can say, oh, if it's an ideal or isentropic turbine or pump, and I know S at the inlet, then I automatically know S at the ideal or isentropic outlet. Oftentimes I can use that information to then fix the state, find H at that ideal outlet, and then maybe use the isentropic efficiency to find H at the real outlet. If it's a subcooled liquid, where for delta H, we would say Cp times delta T is equal to Cp times the natural log of T2 over T1. Here, we say for delta S, it's going to be Ct times for delta H, we'd say Cp delta T, right? But for delta S, what we do is we put in the natural log of T2 over T1. So this is like what we're substituting for the temperature difference. And again here, this is the common assumption, the common mistakes that people make, right? This is why I constantly say this. If it's not a delta T, you have to use Kelvin or Rankine, right? So the natural log of T2 over T1 is going to be much different if T2 is 0 degrees Celsius or 273 degrees Kelvin, right? So use Kelvin. For ideal gases, it gets a little difficult, right? So for delta S, we can never just look up S for an ideal gas in a table, right? So here, we instead, in the table, it says S superscript 0. A common mistake that people make on the exams is they only tell me this S delta S superscript 0, right? Because they think, I don't know what delta S, I don't know how to do this. I'm just going to neglect the fact that that superscript 0 part is there and write this down, right? But that S superscript 0, it's telling us, that's the entropy change, the specific entropy change, only because of temperature. So we still have to do something with the pressure. So I look on my ideal or on my equation sheet, and this equation is there, right? And then we have to put in this R. R is the specific gas constant, which is R bar divided by the molar mass, and then natural log of this pressure ratio, The pressures also have to be absolute pressures, but we rarely deal with gauge pressures in this class. So if you're not specifically told that it's a gauge pressure, you can assume that it's an absolute pressure. Now, ideal gases, right? If we say, oh, the fluid is an ideal gas, then you either say it's variable specific heat, that's this part where you'd look it up on table A22, or it's constant specific heat where you'd use one of these two equations, right? For open systems, we'll typically use this one because we'll often have the pressure ratio. For closed systems, we'll often use this one because we'll have the volume ratios, right? As always, when we use variable specific heat, our answers have better accuracy than if we use constant specific heat. So we suffer in accuracy, but we gain in the fact that we don't have to do any kind of table lookups. Okay, this I just put in here, right? So we talked about delta H for ideal pumps. I'm never going to ask you to derive this on an exam, but just so that you see it. So this is little w dot, right? This is the, I think the textbook will say it's like the power consumed per unit mass flowing through the system, right? Or sometimes you could say specific power, right? It's just going to be delta H, right? But H is really U plus PV, right? So here, because we assume that the temperature is approximately constant across this ideal pump, then, we get that the specific volumes are the same, right? But we're also going to say that the specific internal energies are the same, so that's going to drop out. So then we get this equation that for the pump power, it's m dot times P1V1 minus P2V2. But we've already assumed that the specific volumes are approximately constant because they're subcooled liquids. In the pump, it comes in as subcooled liquid, goes out as subcooled liquid. So here we're going to say that that specific volume is approximately constant because the density or specific volume of water is a weak function of pressure. So then we can say for that ideal pump, it's m dot times little v times delta P. Right, so that's, if you wanted to know or remember where that equation comes from, that's where it comes from, right? For that, this is, I don't know why that slide was there, honestly, because it totally broke the flow of what we were talking about, right? So for ideal gases, right, if we say that it's constant specific heat, right, then we get these equations, right? Now, if it was constant specific heat and isentropic, then you could derive these equations, but you don't need to derive the equations. What you need to know is if you're talking about a process that's isentropic and your working fluid is an ideal gas, you're looking for an equation with K in the exponent, right? And usually I will use one of these first two equations here. If it's a closed system, I'll use this one because it's got volume information in it. And if it's an open system, I'll typically have pressure information, so I would use this one. This one lets us relate the temperatures to the specific volumes, but I don't know if I've ever used this equation, right? And we do have to remember that K is equal to Cp over Cp. So now when we're talking about variable specific heat, I'm not going to ask you to do this on the exam. We haven't really talked about this yet. So I'll go through it now, but it won't be on the exam. We'll start to do this when we talk about internal combustion engines and then further as we're talking about other cycles that use gases as working fluids. But, just like it's got this weird notation for S superscript 0, right? It's also got this PR and VR over here in the table, right? So, if I look on my equation sheet, there's a section of that equation sheet, right? I like to think, I made the sheet, so I like to think that it's well organized, right? But here there's a heading and it says isentropic ideal gas equations. So, if I've got an isentropic ideal gas process, then I should use these equations, right? Now, if I'm going to use variable specific heat, I would use these equations, right? But if this is on the test, I'll ask you to use constant specific heat, but I'll show you how to do this, right? So here, if I knew the pressure ratio and I could fix state 1, right? Let's say state 1 was 200 degrees, right? I could come over here and say, PR is 0.336, right? If I knew what P2 was, then I could find PR2 because this ratio is the same. And it's the same with the volumes. But you don't have to worry about that too much today because it's not on the test. So we'll talk about that more as we get past Rankine cycles and into internal combustion engines. And then these other, if you were looking for where are these equations with K in the exponent on the equation sheet, they're under isentropic ideal gas equations, because you can only use these equations if your working fluid is an ideal gas and it's an isentropic process. Okay, so then we had talked about all of these different processes, and I kept saying, thermo's cool. It's like Lego. You can put these Lego bricks together and do cool stuff, right? And each process is a Lego block, right? So now we actually start doing that, right? We actually start to take these different components and put them together in interesting ways, right? And the first way that we put them together is in this thermodynamic cycle, which we're calling a Rankine cycle, right? So in the Rankine cycle, it's a heat engine, right? Because we're putting heat in, right? It's like a coal power plant, right? The cost of a coal power plant, at least energetically, is that we're burning coal, right? And the energy benefit is that we're producing power on net, right? But we'll learn later that the idea of heat pumps and refrigerators, we can also look at as a series of open systems. But we won't do that till the end of the class, right? So heat pumps and refrigeration systems are kind of the same. It just depends on your perspective, where you're thinking about the energy benefit, right? So when we're generally talking about thermodynamic cycles, here's what we want to do, right? So first, you want to know what the characterization parameter is, right? The good news is, for Rankine cycles, the only characterization parameter we need is isentropic efficiency, right? Then we want to do conservation of mass on all elements. For the 4-component Rankine cycle that we know, all the mass flow rates are going to be equal, because it's going to be steady state, one inlet, one outlet, at least on the hot side everywhere. Then we'll do the first law. Usually we'd expect heat transfer rates to be m dot times h out minus h in, and power to be m dot times h in minus h out. Second law, if required, maybe we're asked, demonstrate that this process is possible, and then you can use the second law and find sigma dot. Then you'll have your symbolic solutions for everything. Then you got to ask yourself, what's the fluid? In a Rankine cycle, the fluid is water, or something like water that's bouncing back and forth across the vapor dome. You go through, you fix all the states, right? You keep track of all that stuff on your state table. Once you have all those H's or S's or whatever you need, you put it back into your symbolic equations, and poof, you got an answer, right? So you can find your actual efficiency, right? So that's going to be net power divided by heat in, right? And then you can divide that by the Carnot efficiency, or look at it compared to the Carnot efficiency. And another way you can say, is this process possible, is if the actual efficiency is less than the Carnot efficiency, well, then we can't say that it's not possible. But if the actual efficiency is better than the Carnot efficiency is like best efficiency you can have. If you've calculated that you can get better than the best efficiency, you did something wrong. Real characterization parameters, right? So always you can define the thermal efficiency as net work divided by heat in, right? Or coefficient of performance is going to be, you're trying to cool down the cooled place. This is for a refrigerator, divided by the net work. That's the energy cost. And for a heat pump, it's going to be the heat transfer on the hot side divided by the net work, right? So, but it's always energy benefit over energy cost, right? So if you can think about it that way, then you don't even really have to remember that these three equations, they kind of collapse down into one equation. Carnot efficiencies, right? We talked about this, how we can substitute the net work in for a heat in minus heat out, and then we can get this equation. And then if I want to move to the ideal or Carnot version of the equation, I can change that ratio of heat transfers to a ratio of temperatures. And I can do that not just for thermal efficiency, but for coefficient of performance as well. Right? Again, anytime you have an equation that's not a delta T, you have to use absolute temperatures. So for Rankine cycles, we'll try to go through this quickly. I'll probably go over a little bit. If you do have to take off, that's fine. I'll post this online later today. So for Rankine cycles, right, we've got these 4 components, right? A turbine, a condenser, a pump, and a boiler. The TS diagram, which I could certainly ask you to draw. You should know how to draw this. will look something like this. When you draw this, if it's part A of a problem, you might not know exactly where this state is going to hit. That's fine if you draw it in the wrong place in your sketch. But as you work through the problem, you'll figure out where that state 2 and 2s are. Turbine produces power. The condenser rejects heat. The pump consumes power. And the boiler adds heat to the system. If I look at my thermal efficiency, what do I need? I need the net power and the heat transfer rate in, right? And if I know the hot and cold temperatures, then I can find the maximum efficiency. Right? Another way I can characterize this cycle is by looking at the backwork ratio. That's recognizing that the power plant is the first consumer of the power plant, and we want to know how much of this turbine power is going just to run the pump so that the cycle can continue to operate. If I do the first law, right, we're going to make some assumptions most of the time, although I could definitely disrupt this, right, make you relax some of these assumptions, right, the same assumptions we talked about before. And what I end up getting in most cases anyway, unless there's something a little bit funny that happens, which I could do, that the turbine and pump power are going to be m dot times h in minus h out, and the heat transfer rates on the hot side and the cold side, if you're solving for q dot, are going to be m dot times h out minus h in. We expect the turbine power to be positive because that's work out. The condenser heat is being rejected, so heat out is negative. The pump is work in is negative, and the boiler is heat in, so heat in is positive. If, like me, you always want to get your power terms from the first law, then you have to remember that net power is not turbine power minus pump power because the pump power is negative, right? So if you do turbine power minus pump power, you'll have like, let's say this is 100 and this is 1, right? You'd have 100 or minus 1. 100 minus minus 1 is 101. You can't have 101 because that's bigger than 100, right? So look at your net power. Your net power has to be less than the turbine power, right? So you take the turbine power and you add it to the pump power. Right? And then, after you do these, you started with your conservation of mass, then you did conservation of energy. Now you've got these equations and you say, what's the fluid? Right? And the fluid in a Rankine cycle is water or something like it. And you fix the states the way that you fix states for water, right? So you're going to look at the vapor dome. You're going to see if it's water A2 or A3 or A4. And if it's a subcooled liquid, the one that people mess up, right, is when they look at the ideal pump, they forget that it's m dot times specific volume times delta P. And that is all that I have for now. We will keep an open class. I'll ask next week what people would prefer for when we have that open class. Whether that would be whether people would prefer it on Wednesday or Thursday. I can't remember what we did last time, if people wanted it the day before or the day of the exam. So I'll ask again next class. So I'm willing to stick around for a couple of minutes if people have questions, but otherwise I have nothing else to talk to you about today, and I will see you tomorrow.
Thank you, Professor. See you tomorrow.
Sounds good.